Now, as of now, we've only really spoken about monoprotic acids. Now, monoprotic acid is an acid that can donate a single H plus ion. Let's look at a few examples. Hydrochloric acid, acetic acid, nitric acid, hydrobromic acid, hydrofluoric acid, chloric acid, and perchloric acid are all examples of monoprotic acids because they can all donate a single H plus ion. Now let's look at the ionization of these acids in water. Let's choose some hypothetical monoprotic acid. So let's choose HA to be our acid. And HA will react in water to produce hydronium and a conjugate base. Now we've spoken about something called Ka, or the acid ionization constant. Now if you don't know what K is, check out the link above. But Ka is basically the product of the concentrations of the product. So the concentration of this guy times the concentration of this guy divided by the concentration of the reactant of this guy. And we said that if our Ka value is high, if it's bigger than 1, that means our acid is a strong acid. And if our Ka is low, if it's less than 1, we're dealing with a weak acid. Now, by strong acid, I simply mean an acid that's willing to dissociate, that's willing to go from this form to this form. So therefore, if our Ka is high, that means the concentration of these guys is high, and the concentration of this guy is low, and that makes sense. Now, let's look at polyprotic acids. Polyprotic acids are those acids that can donate more than one H plus ion. So let's look at a few examples. Sulfuric acid, hydronium ion, phosphoric acid, and carbonic acid are all examples of polyprotic acids. And that's because they all have more than 2 or more than 1 H plus ion that they can donate. This guy has 3 H plus ions that he can donate. So, in the same way that we spoke about ionization reactions of monoprotic acids, we can also talk about the ionization reactions of polyprotic acids. So let's look at a hypothetical example of a polyprotic acid, H2A. Now for H2A, we're not going to have one reaction, we're going to have 2 reactions. And that's because we have 2 potential H's that can be lost to our environment. So H2A will react in water to produce hydronium and our conjugate base. Now let's look at this conjugate base. This conjugate base can either go 2 ways. It can either act as a conjugate base, taking this H back and creating back our acid, or it can act as an acid itself, and it can react with water to produce a second hydronium ion and the final conjugate base. Now the same way we spoke about Ka, or acid ionization constants, for monoprotic acids, we can also talk about Kas of our polyprotic acids, except now we're not going to have one Ka, we're going to have more than one Ka. Each Ka represents a signal reaction. So for this particular polyprotic acids, we have 2 reactions, so we have 2 Kas. And normally, the first Ka will have a higher value than the second Ka, and that's because of the following fact. Now when we go from this acid to this base, we get a -1 charge. When we go from this acid to this base, we get a -2 charge. Which one of these is less stable? Well, this guy. And that's because the more charge we have, the less stability. And so this guy will not want to exist by itself. This guy will want to exist in this form. And so our reaction for this guy is favored this way. And that's why our Ka is much smaller for this reaction than this reaction. And in fact, this reaction is 10,000 times more likely than this reaction. So, in the same way that we spoke about titration curves of monoprotic acids, we can also talk about titration curves of polyprotic acids. So here's our titration curve. Well, the y-axis is pH and the x-axis is volume of base added. Now this curve is for our hypothetical polyprotic acid H2A. Now this guy will have not one equivalence point, but 2 equivalence points. And let's look at what each represents. Let's look at the first one. What the first one represents is it's the point at which all of this guy has been neutralized to this guy. So there's no more of this guy, and 100% of our solution is in this form at this point. Now what the second point means is it's the point at which all of this guy has been neutralized into our final conjugate base. And at this point, at the second equivalence point, all of our solution is in this form. So at this point we notice we have a very high pH. And a high pH means we're in a basic environment. And basic means we don't have a lot of H plus ions. So why is it that at this point this guy really wants to dissociate into this guy? Well, let's examine why. Well, at our high pH or a basic environment, we don't have a lot of H plus, so this guy decreases. So to compensate that, according to Le Chatelier principle, this guy will dissociate. So our equilibrium will be favored this way. And that's exactly why at a high pH, our reaction goes this way, and at a low pH, our reaction goes this way. Because at a low pH, we have a lot of H plus ions. So our equilibrium will be favored this way.